Okay, so here's another example. I kind of modified this from a problem in Hibbeler Mechanics of Materials, problems 865 and 866. And I think this is a really good problem. I ask a lot of problems like this, so I probably would drop some of the other stuff from the class just in favor of doing this problem, if in terms of my priorities. So we have a pipe wrench. I like pipe wrenches. I was a marine engineer, and then on ships, as an engineer on ships, you do a lot of wrench turning and on pipes and that kind of thing. And so anyway, I like that kind of stuff. And so this is a 2-inch outside diameter and 1.5-inch inside diameter pipe. And it's being tightened by this wrench, which is like 12 inches long. And it's hard to see there, but there's 50 pounds being applied right there on the end of the wrench with that 60-degree angle that's right in there. And there's 500 psi inside this pipe, and there's a cap right there, right? So that means that's going to have longitudinal stress because of that. All right. And so we want to find the principal stresses at point A. At point A, right here, I guess they're pointing it, and they're showing it on the inside surface. And I'm not sure that I did it for the inside. Yes, I did. I think at one time I didn't do it, but I'm doing it on the inside surface here for this part. And I could ask you to do it at point B for homework or something along those lines right there, so you could see what the differences are. Would not be an identical problem. So here it is on paper, and I've already done some section properties for you. So I already got the cross-sectional area, something you should be able to do, of what this is going to be right here, and moment of inertia for a circle inside a circle, right? This is pi over 64 d fourth minus d fourth, right? Outside diameter fourth minus inside diameter fourth. And then you know that since it's a symmetrical cross-section circular hollow circle cylinder, it's 2 times I for the polar moment of inertia. So let's see. So I have all of that going for me. I also might want to do some, so this is like the geometry part that a lot of times I would do in the beginning of a problem. If I was working on a problem, I might tackle that first. We also might want to know about the pressure vessel onto the thing, and did I do that? So the thickness of the wall is 0.25 inches. And let's see. So the outside radius of the thing is 1 inch, they tell us that. And the inside radius is 0.75. And either one that you do onto the thing, the thickness over the radius, let's just take it to this one. We know it's 0.25 over 1, or 0.25, therefore thick, right? And even if you did it for 0.75, that would even make it worse, right? So 0.25 and 0.75, and you see that you get 0.33333, which is even more than 0.1. So therefore, yes, it is a thick thing. Now, got to be careful when you're doing loads that you don't get lazy. Draw a free body diagram. So there's several moments taking place here. So this is a door handle problem, right? Even though it's a wrench, it's a door handle problem. So let's do it. Let's do the FBDs in the XZ plane, or the ZY plane. And so let's take a look at it. And it's you can entertain yourself with these and make a nice drawing of the thing, right? And instead of putting the forces like this, let's put a force in that direction and break it into components in that direction. And we know that 50 times the cosine of 60 is going to be 43.30 pounds, and 50 times the sine of 60 is going to be 25, right, pounds. Just get it out of the way, right over to the side of the thing. So this right here is 25 pounds, and this is 43.30 pounds. This distance right here is 12 inches, right in there. And so there's going to be a reaction moment coming, reaction force coming that way, reaction force coming there. Easy enough. You know that this R, A, Y, and R, A, Z are that direction. There's also going to be a moment. I might draw it, because I made the wrench too big right here, I'll draw it like as a big looking thing. And if that's going to, this guy is not going to create a moment. This one is going to create a clockwise moment. Therefore, this should have a counterclockwise moment in terms of our M. And I guess we'll just call it X, which is actually torque, right? We could also call that capital T if we'd like for torque. So the sum of the moments about the x-axis it is, right? Because x is coming that direction, weirdly enough. No offense, Hibblers. We say that we have mx minus 43.30 times 12 equals 0, and our mx, I have it written down somewhere, is 519.6 inch-pounds. All right, so let's see. Let's take a look at the XZ direction. The XZ direction. Do I need the XZ direction? That's one thing. Let's go ahead and do it anyway. It's good practice. So here we go. Here is the pipe coming up there, and then here's the wrench. Right, so there's the wrench, and here's the support, and I didn't leave enough room to, now I'm crowding things up. But here is your 25 pounds happening right there onto the end of the thing. And there's no other loads coming on here now. This distance right there is 10 inches to there. And so here is our reaction, whoops, I didn't draw my coordinate axes. Let's see, I'm looking down that way. I guess this is ZX right there, right? Because we're looking down. There is Z in line with that. X is in line with that. Okay, there's our ZX. So here's our reaction in the Z direction. So it's RAZ, which we know is 25. Here's this moment that's happening right onto there, and this is going clockwise again, so this one must be going counterclockwise. So that's really a lousy place to write that because it looks like it's connected to there, but I'll call this MA, and this is Y, right? That's about the Y axis. So I guess I didn't give this guy a letter, but anyway, as a subscript. But anyway, sum of the moments about the Y equals 0. We get MAY, and then minus 25 times 10 equals 0. MAY is equal to 250 inch-pounds, right? And then lastly, we want to take a look at the XY plane, and it's weird because we're almost kind of tempted to go that way right there, right? That's the XY plane for us, but normally we would have this direction as our XY, right, for the FBD. So we're kind of turning it around and looking at the thing like that. Did I do that? No, I actually did it kind of all messed up right there. Anyway, let's keep it this way, XY. And the only thing that you end up seeing for this one is the 43.30 pounds looking down in that direction. And weirdly enough, I'm looking from this direction over here at it right there. That's why I can see that. I guess I don't know if it matters, but I guess at one time I decided it matters. But anyway, here is my reaction, R A Y, and here is my moment reaction, and that's going counterclockwise, so this one must be going clockwise, and that's going to be my MAZ, right? Because it's about the z-axis, so sum of the moments about the z is equal to 0, counterclockwise is positive, and what I have here is, oh, I didn't put the dimensions here. This is going to be 10 inches right there, right? Is that correct? Yeah, 10 inches right there, sure. And so we say that negative MAZ plus our 43.30 times 10 equals 0. So we can say that MAZ is equal to 433.0 inch-pounds. But just be aware that, like, you know, what was I going to say? I don't know. Just be aware. Sure. We'll go back. Woo! Too many. All right, so now we have to decide. We got all these reactions, but which ones actually matter? Because we're only asked for the stress at A right here, right, which is right there, and it's on the inside. That's like an important type of thing. So looking at this, what kind of which kind of bend, what kind of moment creates bending at A? And looking at this, or maybe even taking our little thin guy right here and seeing at A right here, it's got to be something that pulls it there. So it's got to be about the Z. So this one causes bending stress at A. And if you look at the other one is going to be the one it's this guy from this direction, right? That's pulling it there. It's pushing in here, and it's causing stress here on this side and on that side. But this guy is the neutral axis, right, of the moment that's going about the y-axis right there. So it's all. So we didn't actually have to calculate that moment, but we do need this moment right there. All right. So as we go about to get our stresses, I guess I'll just split up the pages here when I get to the next one. Did I need another? I guess I needed another page to be able to do that. I guess I'll use the back of one of these. All right. So now those are my loads. Now for my stress, right? Axial. No. There's no axial stress on that. Go back to the thing and look. There's nobody pulling in that direction. There's longitudinal stress. We're not, even though that is aligned with the axis, we're not calling that axial stress. We're letting it be its own thing. Bending stress. Bending stress, I'll go bend here. It's going to be MC over I, and we already established that it was going to be this guy, 433, but what's it doing? Is it doing tension or compression? Well, it's going to keep going. You could just even tell by that component that it's going to kind of make this thing bend downwards right there. If we weren't sure, we should draw out the stump, maybe, right? Draw out what you know, after we get done going through this thing and figuring out which way that this thing moves onto the thing, we could draw it back onto the stump, and it might even be better to draw it like maybe in how we're familiar with it, like right there, right? That's how we're looking at this piece, you know, in our orientation to the thing. And this guy, remember, is, you know, this is going to complicate it because we looked at the other side, so that makes it like a little bit more complicated. So it's kind of even better just to take a glance at the thing and to know that we're coming down that way right there, right? Or maybe I should draw it that way right there. Is a little bit better. onto this. So we can see that it's going to be tension. Another thing we have to be careful of is this. We might even want to write this as my over I, because the actual fiber that we're doing this to is not to the outside. It's to the inside of the pipe, right? So the moment is 433.0. C in this case is the inside radius, or 0.75, divided by our I, which we were given 0.5369. And what we end up finding, we have 604.9 psi, and that's tension, right? We're not dealing with really large numbers. Maybe we should have increased our values onto this, but I was using somebody else's stuff. All right, so moving on with this very important problem, we now go to torque. Let's go to shear. All right, so torque, we're going to have TR over J, and once again, okay, the torque is going to be the one that's here, right? It's the one, it's just like a wrench. It's a wrench, it's turning this thing, it's along this axis, so it's twisting it. So it's 519.6. But remember, this R is to the measured to the point from the center to the point we care about. So it too is 0.75. And then J was something that we were given up here as 1.074. So we get that torque, and it's 362.8 psi. Now, let me go transverse. Transverse. Now, for a hollow cross-section, if we look it up in Chapter 3 in that one table, we'll find for a hollow cylinder, you get 2V over A. Right? So, which V, though? That's the important thing. Well, remember that this is at the top of the thing. So the force that's going through it doesn't cause shear. It's the force that's coming from the side. And that's going to be this one right here. So it ends up being that 25, right? So we get 25 divided by A, when A was given as 1.374, and that's going to be equal to, and by the way, this is an approximation, because unfortunately this guy right here, go approx, this guy right here is actually to the outside. So we're doing on the inside. So this is an approximation. But look how small this is, 36.39 psi. Maybe not important. All right, and then, okay, so those are the basic ones, but now it's also a pressure vessel. So let's try that out. Now, the original problem didn't have that, and it's a thick-walled pressure vessel. So let's start out with longitudinal. That has the equation of P times RI squared, yep, and then RO squared minus RI squared. And because of that, let's see, we said it was 500 psi, 0.75 squared, divide by 1 squared minus 0.75 squared. And that's going to be equal to 64.2, no, 642.9. No, is that right? Yep. 642.9 psi, and it's tension, right? It's aligned with the x-axis, but it's tension. And then we could get the hoop right here, right? Which I guess I just go T. It's all of this. I'll write it here. 1 plus, and then RO squared divided by RI squared. But we already know that right there is that, right? So it's going to be the 642.9 times 1 plus, and so we're going to have 1 squared over 0.75 squared. So this is going to be something greater than 2 right here, right? And so we get 1,786 psi. And then the last one is going to be our radial, and that's just going to be 500 psi in compression. So wow, we have a lot of stresses, a lot of different things taking place. So let's go back and take a look at a little section, draw a little square out through there. We'll try to align him with the coordinate axes to try to keep it straight, right? So this one was really weird because it was going Z, Y, X, Z, Y, X, right? So things that are happening in the X direction. Whoops, I didn't do a very good job. I guess it's good enough. X direction right there, right? All right, so in the X direction, we had bending and we had longitudinal. And bending was tension, right? And bending is aligned with the X because it's pulling here. So it's pulling in the X direction. So this is going to be 604.9 plus is going to be the longitudinal, right? It's trying to get longer in the X direction. So that is, where'd you go? 642.9. So you end up being 1,248 psi. How about in this direction, right there? Whoop, bad move. Should look a little closer. In that direction, the Y direction, that's actually aligned with the radial. So that one right there is simply 500 psi. This one right here, this is our hoop. And that is simply going to be 1,786 psi. Now here comes some real thought that we really have to put into here. What about the shear? How is that shear taking place? First off, what face on this little cube is the shear taking place onto the thing? Well, look, like you could even just kind of like sketch out, right? The shear is coming around this way, and actually in this twisting that this thing is doing, it's actually coming this way, right? It's twisting about that way, about the face. So it's actually going across the face of that element that's up here at the top. It's going across that face. So that's there. But which direction is the transverse shear going? The transverse shear is from this direction right here, right? So the transverse is taking place from this force coming across there. So it's actually going across the face in the opposite direction. So this one right here is going to be the torsional shear, 362.8, minus the transverse, which was 36.39. We have to remember that's an approximation because we're looking at a point that's on the inside surface, whereas the transverse is really giving us what's on the outside surface. But the thickness is kind of small, you know, relatively speaking. It's and it's all over a small value anyway. So but recognize it's an approximation. It's not something that we want to hang our hat on. But fortunately, it's not it's not a large number to make a big amount of difference right there. So doing all of that, let's only look at the XZ direction. Let's summarize this in the XZ direction. I think I made it this way right here. Let's see, because I want to look down. I'm going to look down on this element, right, so that I don't have to see the radial. We'll recognize that the radial is there. So that direction right there is Z, and this direction is X right there. So we're looking at that face right there. We're looking down upon it. And if that's the case, that goes in that direction, right? And this in the Z direction is the largest value there. There's your 1786 psi. And over here, I'm going to write over in this 326.6 psi. And then this is the longitudinal, or not longitudinal, but the sum total of the one in the X direction. And I'll put it up at the top, 1,248 psi. Now we have to do a Mohr circle. We don't have to do it on graph paper. It's nice to make it nice and neat, as neat as you can. Let's see. It's tension and tension. So it's going to be over here on this right-hand side. This is quite smaller compared to that. So let's say 17 is somewhere over here, 1786, we'll call it 1800, 1200's over here, 300 is much smaller than that, right? So it's something like in there and then there. And so on this face right here, we have the tension, and this one's clockwise, so he's going to be up here. And on this face, it's going to be here, but we're going to be down right there, right? So we kind of draw in this, and there we're going to have to fudge some stuff in there because I'm not doing it on a graph paper, right? I'm just doing it to try to get a good circle. And so we could find C, right? There's C right there. And well, I'm trying not to get in the way of my future circles. Maybe I'll write it over to the side over here. C is going to be equal to the average, 1786 plus 1248 divided by 2. And so C is equal to 1517. Now we want R. We could choose either one for R, either this top right here or this one right here. I'm going to choose that one. R is going to be the square root, and it's going to be my C, 1517, minus this guy, which is my 1248 squared, plus my 326.6 squared, and so I end up getting a R of 423.1 psi. So my sigma 1 is going to be C plus R. I would say a lot of times I would say maybe sigma A is that, right? That's what I had said in the previous classes. So I had a 1517 plus my 423.1, and that ends up coming to 1,940 psi. And that's going to be the one that's furthest over here, right? So maybe I should draw my Mohr circles, and I'm doing my freehand sketch thing there. Boom. Sigma 1, sigma 2, sigma 3 is actually going to be way the heck over here. It's going to be 500, right? So that's sigma 3. I should label it that way right there. So for my, mess around with this until I get the right thing. I could plan it out, but let's see. Let me see. I'll just mess with it until it gets right. Oh, that almost came out right. Look at that. There you go. Not a very good one to label because it's up at the top right there. Darn. But tau abs max is up here, up on top of that. This guy, I'm going to guesstimate. That's the middle. Did a terrible job with that one. Got cocky. It's too easy last time. Oh. There we go. Something like that. There's our 3 more circles. Let's get the values. Finish up with the values. Sigma B is C minus R. So that's going to be the 1517 minus 423.1. And that comes out to 1094 PSI. And we can recognize that's sigma 1. This is sigma 2. And then sigma 3 is 500 PSI compression. And I should have put a tension inside there. I'm getting tired and I'm hungry. And I'm getting like, I don't feel like doing this. Let's finish one more thing though. Let's go to the tau abs max. The tau abs max is going to be that sigma 1 minus sigma 3 divided by 2, or that's going to be our 1940 minus 500 divided by 2. So we get 1220 PSI. And that's the thing that we are going to use to evaluate all of this. So we really should, if we were going to be good students and try to get our grades, good grades, write the whole thing out again. 1940 PSI tension. Sigma 2 is 1094 PSI tension. Sigma 3 is 500 PSI compression, and tau abs max is equal to 1220 PSI. Don't put a tension next to that, and here, box it out. And there is our answer. It's a long problem. It's a very long and complicated problem, but that's what you're here to do, right? Is to solve hard problems, picking them apart, methodically picking the thing apart and observing and getting the directions of the stuff correct. I went ahead and made a SolidWorks model out of this. The problem is already 32 minutes long, but let's see if you have a little bit more patience. And so I made, I did a couple little tricky things as part of this. So first off, I went ahead and made some split lines onto this right here, so you can't quite see them there. But I put in the advantage of split lines is it allows you to like make it so that you could pick when it meshes, it has to mesh with a node exactly where you want it to be. And we want to pick a point that's on the inside. I also made the thing like 2 inches longer over here, and I made a cut right there with my split line so my boundary condition wouldn't interfere with my results. And I also cut it on the inside, right? So there is one single point right here that exactly matches up with our point. I made sure that my when I built this thing, that this thing, like the center of this is the 10 inches away from the point that we care about. And then when I put the loading onto it, you'll notice, well, first off, I put pressure all along the inside right there. And I did put pressure on the back surface. Let me double check. Did I? I don't see it. Now I'm starting to wonder. Ooh, I don't see that pressure in there. Let me go back in there. I think I put pressure in there, but I don't see the symbol for it. Let's double check. Oh no, there it is. Okay. When I backed up, you can kind of see the arrows. They're showing up now. It is on there. And then lastly, when it went to put a load onto this piece, I put the 25 pounds going in that direction, and then the 43.3 in that direction. All right, and then I gave it a mesh. Let's see. Let's show the mesh. Fairly fine. I was going to tune it a little bit. At least I got some, like a couple layers, just to. Yes, just a second. I'm recording a video. What was I saying? Damn it. Oh yeah, okay. So let's see. All right. So okay. So the solution to this. Let me just get the plot points out right here. Plot point, and hopefully I can grab a hold of that point right there. Let's see, right there. Boom. This is von Mises stress right now, and we haven't introduced that. So maybe this would be good to refer back to later on. So this is just a single value that's supposed to represent all of those stresses. We condense the stress into one particular thing. We call it von Mises stress, and it's very useful to us. It's the default output in FEA because it's a nice single value that we can look at. And but I can change like this to be the x direction, or no, the x direction. So let me see if I change this in the x direction, the normal stress in the x direction. Let's see what value it gives us. Let's see how close we got in the plot tools, and we'll go to probe, and we'll zoom in onto there, and boom. We got 2,328. No, that's node number. Duh. I messed up. I was looking at the wrong thing before. I go 1,260. What am I predicting in here? I said I had 1,248. That's actually pretty good. We could actually attempt to look at the hoop. We could see what the hoop says we're going to be. That would be in the stresses in the z direction in this one. So I'm going to edit my definition and go to the z direction. And that's the last one I'll do as part of this. And maybe we'll investigate this in another time, in another way. But let's see. Let's go to the probe and go up into here. Wish I could edit that other thing out. 1,787. And sure enough, my hoop was 1,786. That's dead nuts on, really. Okay, well, so that's going to be it for this video. Hopefully, you'll be able to follow this. I know it's a complicated problem. It's very frustrating for students because there's a lot of stuff to try to digest. But you have to work through problems and practice them. Struggle a little bit, overcome the struggle, and then things are going to start to, if they don't already, going to start to make sense, and you'll be able to like start tackling the really tough problems and using the fancy software to really solve real world problems. And that's what I think is the coolest part about being a mechanical engineer. So take care, and let's go eat some dinner.